In the last lecture, we talked about model hierarchy. That is, we have so far covered a simple climate model for the global mean temperature. That's called the zero-dimension model. And if you want to get more details about how temperature varies with height or with latitude, you go to one-dimension model. We'll cover a part of it later. Or you want to get both vertical and, let's say, latitude, then you can go to 2 dimensions. But ideally, you want to cover both vertical, latitude and longitude to get a global picture of how temperature is changing with height, with latitude, longitude. This is called the 3-dimension model, which can be integrated to a steady state. But the most ambitious model are those in which you have vertical, latitude, longitude, and in time. You evolve in time. For example, you can have a model which starts at 1850 and integrates the model up to 2020, and we see how temperature of the earth varies over time and how it responds to changes in incoming radiation, changes in carbon dioxide and volcanic eruption, for example. So this is the most ambitious model. It's computationally very expensive, very complex, and I wanted to show a few examples of this model in this lecture for you to get an idea how these models are used. Now, these models have lots of components. The first is radiation, which we already discussed in the last few lectures. So you take into account radiation exchange in the vertical, in the horizontal, roll of clouds, roll of gases, all that accounted for in the radiation module. Then the other part, which we have not discussed so far, is dynamics, because in the Earth's atmosphere, winds move both in vertical, horizontal, latitude, longitude, and they transport carbon dioxide, water vapor, and all this have to be accounted for, both in the ocean and in the atmosphere. So this is computationally very expensive and very important to understand how climate changes with latitude and height. Okay? Then we also have to understand how energy is exchanged between the surface of the earth, land as well as ocean, with the atmosphere. Okay? How ice on land or ocean changes the albedo. So these are called surface processes. And finally, you need to understand atmospheric chemistry, because in the Earth's atmosphere, due to natural processes, you have photosynthesis, which consumes CO2, combustion, which releases CO2, and CO2 moves around the earth due to winds. So all these are in the chemistry module. You can see there are 4 major modules: radiation, dynamics, surface and chemistry, both ocean and land and atmosphere, and all these have to be combined to run the model. Now, this can be shown schematically as follows. The most common models are so-called coupled atmospheric ocean general circulation models, which have both atmospheric model and ocean model. Combined, we call them climate models. In addition, you must have hydrology, lakes, evaporation, rivers. Those are called land surface models. And these two are combined, and you have a water cycle, a carbon cycle, and biogeochemistry. What happens in the ocean, how the chemistry of the ocean changes, and chemistry and the ecosystem also included. And all these, along with more modern ones, which you want to look at past climate, you must take into account changes in geology, for example. So these are called Earth system models, which include everything. Okay? And at the bottom, you can see the amount of computational effort it takes, from megaflop to petaflops. Okay? So some centers run these very complex models for hundreds of years to understand how geology interacts with Earth's climate. Now, you must also understand that although there are individual models for land, atmosphere, thermodynamics, dynamics, ocean, all these have to interact with each other. So you have interfaces between land and sea ice, land and atmosphere, land and ocean. So this coupler which couples all these different components is very critical. So that plays a very important role in ensuring that you have a realistic simulation of climate. So this is an example of how the coupler works in a simple case. You have atmospheric model at the top, ocean model at the bottom, which it takes into account all the circulation that occurs due to winds in the atmosphere and the ocean. Then we have to couple changes in the ocean to change the atmosphere through changes in sea surface temperature, sea surface salinity, sea ice, wind stress, wind acting on the ocean, rainfall as evaporation, and the heat transfer. Okay, all these do the interaction with the ocean and atmosphere. Okay, this is a big challenge because the response time of the atmosphere is much smaller. Atmospheric mass is very low. Ocean is very massive. It is much more massive than atmosphere because water has density 1,000 times larger than air, and ocean covers most of the earth. So since the response time of the two are very different, you have to make sure that these are coupled properly, because one system, atmosphere, is responding very rapidly, somewhat chaotically, while ocean responds slowly. Okay, so these challenges have been tackled, and now today models are able to interface these two correctly. Okay, so you have atmospheric GCM, you have chemistry model which transports the carbon dioxide and other gases, and ocean contains biogeochemistry, sea ice, and land contains land ecology, biogeochemistry, and physics takes into account changes in land albedo, vegetation, hydrology, lakes, rivers, and so on. All these are coupled in these models. Now to show it in another way, you have atmosphere in which your equations of thermodynamics and radiation, equations of motion, Newton's laws. You have to take care of turbulence, which is pretty complicated. So you approximate it, it's called parameterization. And you have to worry about water being converted from vapor to liquid to ice and becoming cloud. And this is a part, as I mentioned earlier, is not well represented because clouds are very small. So you have to approximate it, it's called parameterization. And all these have to interact with what's going on in the ocean below, okay, through evaporation, rainfall, heat transfer from ocean to atmosphere, from turbulent heat transport, and the atmosphere affects the ocean circulation through wind stress, and then the rainfall has to run off from land into ocean. So pretty complicated interaction going on. All these are accounted for. Now just to give you one sample, in the case of atmosphere we have the east-west motion, so-called the zonal wind. It takes into account the Coriolis force that acts in a rotating earth, pressure gradient, and various stresses which act on the this one, and rate of change of velocity. Same thing in the north-south direction. In the vertical, normally we assume hydrostatics because the vertical motion of the atmosphere is very slow. So in most situations, atmosphere is in hydrostatic equilibrium, except when there is a strong system like tornado or cyclone, then we have to change it slightly. But most of the time for climate simulation, we assume hydrostatic balance. And of course, you need mass conservation, very critical. The air moving in the horizontal and vertical direction has to conserve mass at every volume. Okay, and then this is of course energy conservation, and finally of course you have ideal gas law, which is used for the atmosphere. So you have 7 equations and 7 unknowns, and we integrate. This is one example to show you how complicated these models are. So because these models are so complicated, the model that you choose to understand a certain part of the Earth climate system has to be chosen carefully. and it depends on the application. You cannot choose any model for any purpose. When you choose a model, you must ask what is that you are trying to simulate, and for that simulation, which components of the model are to be represented accurately, which can be done approximately. So this requires a lot of experience, and so now I am saying this because today you can download many climate models from some website and run it, and many people do it, but if you choose the wrong model, you will get the wrong answer. So you must be very careful in choosing a model and how you run it. To give you an example, our model has scales going from 1 meter to 10 to the power of 8 meters, and time scale from 1 second to 10 to the power of 10 seconds, so many years. Okay? And in the present course, our focus is on long-term climate. So we look at these scales years and longer and thousands of kilometers long. But if you are interested in a cyclone, then you have to be in this scale. Okay? And if you are interested in tornado, you have to go to smaller scale. So you have to choose what time scale you are interested in and appropriate spatial scale. They are connected, they are not independent. Okay? So you have to choose your application, choose for what time scales you want to simulate, and choose the appropriate model which will take care of that time scale along with that spatial scale. Just to give an example, suppose you want to simulate the climate of Bangalore. Okay? Bangalore is a very unique climate. It is somewhat cool in January, then temperature rises rapidly. So by the time you come to April, it is very hot. Not hot compared to Chennai, but it is hot for those who stay in Bangalore. Then it reaches a maximum around May, then the clouds and rain come, it rapidly declines in temperature, and by the time we reach June, July, it becomes quite cool again and remains cool till about October, then it cools further due to the fact that we are in winter. Okay? Now this temperature variation with season, if you want to simulate correctly, you need to model the fact that Bangalore has many buildings, urban areas, and you have to model them correctly, and they affect the way water flows through Bangalore. But there are also green areas like parks and so on. There you have to simulate the vegetation, how it runs off from the rainfall. So if you don't represent these things in your model, then you won't get this answer. Okay? So the climate model you choose has to appropriate to the application that you have in mind. So you have to spend a lot of time to figure out what is the right model for your purpose. So let me give an example of what has been done with climate models over the last 30-40 years. So people have simulated the climate of the last 100 years, because if you want to predict what will happen in the future, you must be able to correctly predict the past, the immediate past at least. So you have to get the mean state correctly and how it varies over all these years. So a lot of models have been run for the last 100 years to make sure the model correctly simulates the climate of the earth from 1850 to today. Okay? Then people have got more ambitious. They want to simulate the climate of the last 20,000 years. For example, the last glacial maximum, or even very long time past. So or the last 1,000 years. Okay? So these are now getting to be quite common, because we have a lot of proxy data will tell us what happened in the earth 1,000 years back, 10,000 years back. So we want to see whether our models are good enough to simulate the past climate. Then to understand climate models, which are very complex, you run idealized cases. You suddenly increase CO2 by a factor of 2 and see what happens. Or you suddenly add water near Greenland to see what will happen if ice melts rapidly in Greenland and how it affects the ocean circulation. So these ideal models are run to understand specific aspects of the Earth's climate. Okay? So there are all kinds of model simulation which are related to what you want to understand about the model. You have built a complex model, but it is a very complex beast, and you have to spend a lot of time understanding how this model behaves. Now, to give you an example of how people have done, now many models are run for the last 100 years, and there are about 58 climate model simulations for the last 100 years, and these small yellow lines are many simulations of each model. Then the average of those is the red line called the ensemble mean of all the simulations, and the black is the observed global mean temperature. So you can see that models are correctly simulating the warming of the last 100 years, but they don't get specific periods correctly. Okay. Now, this lack of agreement over a few years may be on account of models' weaknesses or limitations, or could also be that in the past we didn't have too many observations. Remember, before 1960, the models, the observations were not that many. So there are lots of missing data over oceans, for example. But in the last 60 years, you can see the models are doing quite well, but still in certain periods they are not so good. For example, the volcano Pinatubo erupted in June 1991, and the model simulation of the cooling is a little too high compared to observations. Now, this could be due to model limitations, or it could also be due to the fact that we did not correctly put in the data from volcano. When a volcano erupts, you have to get the right data of the kind of particles it put into the atmosphere, its properties, its amount. So there could be some errors there also. Okay, and also remember, when you look at year-to-year variation, there is energy exchange between the ocean and the atmosphere, and these are complex processes, and these models are not simulating well right now, although they are improving. So you can see that the last 40-year trend is correctly simulated, but any 1 year there are problems. Okay, for example, this large warming that is observed here in the late 90s due to El Nino, and the models don't seem to get correctly. So what you must understand is models are quite good for global mean temperature over a long time scale, 10 years, 20 years and so on, but not good for year-to-year variation. So these models can be used to predict what will happen 50 years from now. So the global negotiations about climate change are based on these models, and for that they are okay. But if you want to know what will happen next year, the model may not be so good. Okay. Now, to show how these models have been used by the Intergovernmental Panel on Climate Change, here is one example of the models which took part in so-called CMIP-5 simulation, coupled model intercomparison project, in which many models ran the same type of simulations for comparison, and the models were run twice, once without changing CO2, keeping CO2 at the pre-industrial value of 280 parts per million for about 150 years, and then the model was run again with increasing CO2 as observed, that is the red one, which is the mean of 36 models, okay, and black one is the observation. Now, what you see very nicely is that when you run the model with increase in CO2, it shows correctly the large warming that has occurred in the last 70 years. Don't look at year to year, look at the trend. Okay, it does very well. And the model also shows that the CO2 had not increased, we did not have an industrial revolution, then temperature would not have changed at all. It would have remained around plus or minus 0.2 degrees of the temperature in 1890. Okay, so this model has been very useful to show clearly that the warming of about 1 degree in the last 60 years is mainly on account of the increase in CO2 and not due to any other natural causes. Okay, so these models are useful for this purpose, to test a hypothesis, because I must tell you, 30 years back many people had doubts whether the warming that's going on is due to human induced climate change or due to natural causes. today we can say with great confidence that what we are seeing today is a consequence of the increase in CO2 caused by human actions. So these models were used for that purpose. But the same model may not be good to know what will happen next year. So you must understand the strength as well as limitation. Those people who don't believe in climate models will say, we don't trust these models because it cannot get me next year's temperature. But if your aim is to understand whether the increase in CO2 is causing global warming, then you don't have to worry about next year's temperature. You have to worry about the temperature change over the next 50 years. For that, these models are very good. Okay? So remember the subtle differences between application. Okay? Certain models are good for certain applications, but not so good for some other applications. Now I'm going to give you an example of some simulations done by Eiko Voigt and Joachim Marcuse from Germany, published in Climate Dynamics about 15 years ago, to show how Earth can go from present climate to snowball Earth if we change the incoming radiation. This is a thought experiment. It doesn't happen in real world. So you just understand how sensitive the Earth's climate is to incoming radiation. Okay. So these TSI is total solar irradiance coming in. Okay. 75 means 25% below the present value of 1364 watts per meter squared. If we reduce the solar incoming radiation by 25%, this model says for all ocean covered Earth, simple model, that within 100 years ocean is completely ice covered. Okay, within 100 years. On the other hand, if you don't bring down the radiation that rapidly, but bring it down only by 6%, then the sea ice will change very slowly. Even after 1,000 years, you will not see a rapid increase in sea ice. So you can see the very big difference between 6% change and 25% change. And in between there are other cases, 9%, 13%, and no CO2. No CO2 in this case, you keep the solar radiation constant, but suddenly remove CO2. If you remove CO2, within 200 years, Earth becomes completely ice covered. So I want you to remember this case because it shows the very important role played by carbon dioxide in Earth's climate. If you remove all the carbon dioxide from the Earth, the 420 ppm that's there now, within 200-250 years, Earth will be ice covered. So carbon dioxide is a very important part of Earth's climate. Although we are concerned about its increase beyond the normal value, but CO2 is necessary to have a stable climate and climate in which you can practice agriculture. So CO2 is not a villain. The villain is that we are increasing CO2 too rapidly. So I want you to remember that if CO2 is removed suddenly, Earth's climate will change rapidly. Within 200 years, we'll have ice covered Earth. So this simulation was very useful to understand this. This is not a real Earth, it is only ocean covered Earth, but gives you a lot of insight about the time scales by which Earth's climate can change, is the abrupt change in either incoming radiation or carbon dioxide. Okay. Now there are others who have done similar simulations. Okay. And here I am showing this only to show you how changes in Earth can be abrupt. As you go on reducing the incoming solar radiation by 1%, 2% and so on, the ice cover increases slowly and you go up to 90% here. In about 700 years, Earth is 50% covered with ice, okay, all ocean covered Earth. But from 90 you go to 89, suddenly it jumps rapidly to 100%. This is called bifurcation. This shows that under certain conditions, the Earth's climate can change very rapidly. So I want you to understand this very nice feature. From here to here, there is a change, but a very slow change. From here to here also changes are not very rapid, but from here to here it jumps. This is called the tipping point. We will talk about it more in the future, because this is what everyone is concerned. As we are increasing CO2 rapidly, will there be a tipping point beyond which the Earth climate will change so rapidly that we can do nothing further. Okay? This is a very serious matter, and this issue must be understood by every human being to realize that we cannot afford to play around with Earth's climate, because there are certain situations where the Earth will suddenly jump from one state to another state. Now here is the other example which is very interesting, that as you go on reducing the amount of carbon dioxide, you reach a point around 17.5 ppm when the climate suddenly starts going to all ice covered. Otherwise, if you change to 70, 30 and so on, it stabilizes to ice cover with 50% of the Earth. But beyond some point, again, suddenly it starts increasing rapidly. This is called runaway effect. Okay? That is, it reaches some tipping point in which, this I will discuss in more detail when I discuss snowball Earth in a later lecture, that the snowball Earth can only happen under certain unusual conditions, and one of them is very low carbon dioxide content. Okay? But I want you to appreciate that these changes are changes over thousands of years. They are slow, so we may not worry about it. But when the CO2 content goes up above a certain value, it suddenly starts going to a snowball Earth. Okay? This point will be discussed further later. Now I want to discuss another extreme case which has been published recently by Heinemann et al. In the Climate of the Past journal, published about 15 years ago, and this is called the Periocene-Eocene maximum. This period is very important because at that time the amount of CO2 was probably around 560 parts per million, double the pre-industrial value. So we on Earth are pushing towards that value because we are putting out CO2 by a large amount. Okay? So it's good to know what will happen. So they ran the model with the present climate 278 ppm and a future climate of 560 ppm. Okay? All the other quantities were roughly same. Okay? And various quantities are given here, you don't have to worry about it. So they wanted to know, if you suddenly increase CO2 from 270 to 560, what kind of climate will you get? It will be similar to what we have, what happened in the past. Now you must remember that 55 million years ago, the Earth's geography was not same as present. India was below the equator. Here is India. Okay? And Africa was not joined to Europe. South America, North America were not joined. So all these you have to, so this model took care of all these geographic features, and the model simulated the temperature 55 million years ago and compared with proxy data. Proxy data obtained from sediments in the ocean core, and these are some samples that were taken from the present ocean at the bottom, and they give you a rough idea of what the temperature was. And notice that the value given in numbers compared with the table which gives the model simulation, they are not perfect, but they are quite close. So showing that this model's ability to simulate the climate 55 million years ago, when the Earth was having CO2 of 560 parts per million, is quite realistic. Okay? So these models are getting pretty accurate in simulating climate change due to increase in CO2. Okay? So I want you to remember that. And so although the models have done this very well, one is happy, but we have to understand what caused those changes. It's not enough to say models are done well, I'm very happy. The model may have got the right answer for the wrong reason. That can happen. So here you see the model albedo went from around 0.3 in the present climate, 0.32 to 0.29, not much change, about 10%. And the model surface albedo went down more because melting of ice, because it was a warmer climate. Okay, the climate was about 9 degrees warmer, and effective emissivity, which I discussed in the last class, that went down also substantially. So now this is some idea, but it is good to relate it to what we learned from the zero dimension model that we did. So this is the simple model they use, although I have criticized it. Still it is useful. Left hand side is the radiation absorbed from the sun, the right hand side is the radiation emitted to space. F is the effective emissivity. So looking at all the model data, you can find out how much F changed, how much rho changed, and how much each contributed to the change. Okay, the model showed a 9.5 degree warmer. If you run a simple model of the kind discussed in the last two lectures, the energy balance model, you will not get the same answer because the model is simple. You will get close to the answer within 1 degree. Okay, so now we can ask, this 8.5 change is due to change in emissivity or change in albedo. So based on the energy balance model, we can show that 5.7 Kelvin change is due to change in effective emissivity, this term, and 2.8 degree is due to melting of ice and changing in albedo and clouds. Okay, we are able to understand little better the complex changes that took place in terms of changes in energy absorbed in the sun and changes in energy going to space. Okay, so clouds affected the albedo and so did ice, and the amount of water vapor and carbon dioxide changed in the past, and that also changed the effective emissivity. Now that is best put on this graphical diagram. The effective emissivity is the x-axis and albedo rho is in the y-axis, and the present climate is here 288 Kelvin, and the past climate, the warmer climate, which occurred 55 million years ago, is along this path, but that can be broken up into change due to emissivity, change due to albedo. What is seen that change in emissivity is twice as important as change in albedo. So that shows that atmospheric emissivity changes are very critical. So that shows the importance of carbon dioxide and water vapor, and also important of ice, but tells you that 2/3 is due to CO2 and water vapor and 1/3 due to ice melting. So now I hope you appreciate that although the simple zero dimension model is very limited, it helps us to understand a complex model. If you don't do that, if you don't understand the complex model, it may have got the right result for the wrong reason. Okay, so we have to use both a complex model and a simple model together to understand the Earth's complex climate system. Okay, with that, I want to show one more result from this model. The difference between the past climate and the pre-industrial climate, that is 1850, how it changes with latitude. So you must remember that when climate changes, the largest changes occur in the Antarctic and the Arctic, not in our region. In our region maybe 3-4 degrees change, but Antarctic and Arctic will undergo 20-30 degrees change in temperature. So we are already seeing that. If you go to Greenland or Siberia, they are having changes of the order of 4 degrees Kelvin. Okay, well, we are seeing 1 or 2 degrees. So models are capturing that changes with latitude quite well. Okay, so with that I will conclude this, and I will also show you that these models have been used to predict what happens if you change the CO2 to 4 times the amount present, or 3 times or 2 times, and what if it goes down from 560 to 280? All these they have done. I will show you one example of that, and you can see that from 560, the Paleocene climate, if you bring it down to 280, temperature will go down to the present value. If you keep it constant, remain same. If you increase it to 840, it will go to the Paleocene, Eocene temperature maximum. But if you increase it to 1120, it will start increasing and go into a runaway greenhouse. That is, temperature will never stop increasing. Okay, so this is a cause of concern. Although this modeling is not easy, so this model is able to show that we need to be careful. If you go on increasing CO2, there is a possibility that Earth's climate will go on increasing forever, and we may have no control over it. So in that note, I will conclude my discussion on this topic, and we will go to the next lecture, where we will look at how different feedbacks in the Earth climate system will affect the Earth's climate. Thank you.